Okay, so we'll take a look at one more example before we wrap this section up. We've got a linear transformation S, and it goes from R3 to R3, and it's defined again in terms of a matrix, or through multiplication by a matrix, and that matrix is given by this 3 by 3 matrix here. Okay, so part A is the same sort of thing as last time. We're asked to evaluate the transformation at a single input vector. So if we want to evaluate S of 1, 2, 3, all we have to do is just multiply the vector 1, 2, 3 by the matrix A. So that will result in this. Okay, so, well, what happens? By definition, we're going to go 1 times the first column of A, which is 1, 0, 0, plus 2 times the second column of A, which is 0, 1, 0, and then plus 3 times the third column of A, which is 0, 0, 0. Okay, and then what's that going to give us? We'll just have 1, 0, 0 plus 0, 2, 0. And if you add those together, you get 1, 2, 0. So that's indisputably the result. But if you just kind of take a step back and say, okay, well, what did S do? Try to describe it in words. What did it seem to do to this vector 1, 2, 3? So we started with 1, 2, 3, and now we have 1, 2, 0. All right, well, it looks like the first and second coordinates were just completely left alone. And the third coordinate was kind of, in some sense, it was just thrown away and replaced with 0. So keep that in mind, okay, for the next part here. So, okay, well, let's put a box around that because that's S of 1, 2, 3. That's what we were asked to find. In part B, so what do we want to do? Now we want to work backwards again. We want to find a vector x such that S of x is this three-dimensional vector 8, negative 5, and 0. So let's kind of do the same thing we did last time. We'll let x be given in terms of some unknown coordinates, and then we'll just figure out what those coordinates would have to be. So we'll let that be a three-dimensional vector, and what we want is S of x1, or I'll just write it like this. I'll write it like the question did for now. I'll just say we want S of x to be 8, negative 5, 0. So what that's going to look like, now we can write it the more verbose version. So S of x1, x2, x3, that's got to be equal to 8, negative 5, and 0. Okay, well, let's replace this with what its definition is. So S of a vector is replaced with A multiplied by that vector. So it's going to become this vector multiplied by x1, x2, x3. So we'll have 1, 0, 0. This is just the matrix A. And that's going to be multiplied by the vector x. And is going to give us, through that multiplication, it's supposed to give us 8, negative 5, and 0. Okay, again, same sort of situation. This is a matrix equation. All right, this is a matrix equation with coefficient matrix given by exactly A, again, and the constant column is just this exact vector here that we want to end up with. So you can solve this system by writing down an augmented matrix. And how about I'll do it, yeah, I'll do it down here. So we'll have 1, 0, 0, 0, 1, 0, 0, 0, 0, and then 8, negative 5, and 0. Okay, and hey, notice, here's a comment. Let's just notice this. You got a row of zeros. Okay, so that's no problem. That we're probably gonna, looks like we're gonna have a parameter. But just notice, if this had been anything else, this system would have no solution, wouldn't it? If this had been a 2, let's say, then this would be a contradictory row, and this linear system would have no equation. Or in other words, this linear system would have no solution, is what I meant to say. Or equivalently, this equation would have no solution. And if that were the case, then, well, then we'd have to come back and say this is impossible. Okay, so just keep that in your pocket. Okay, so, all right. Now let's write down the general solution to this. We've got one parameter. We've got a free variable. X3 is going to be a free variable, so X3 can be S. And then we're going to get X2 is equal to -5, and x1 is equal to 8. So our vector x that we want, we'll put these values together. It's going to be 8, -5, and then this parameter s, where s is arbitrary, any real number. Let's reflect on that now. How does that fit in with what we observed in part A? When we looked at part A, it seems like what S did, at least in this case, doesn't, just because it did it in one case doesn't mean it's always going to work, but it certainly doesn't help to make this observation. It seems to be that S just took the third coordinate of the input vector and replaced it with 0. So just threw that coordinate away. Not completely threw it away, like you just replaced it with the number 0. So whatever non-zero value was there got thrown away and replaced with 0. So if you were to assume for the moment that S does that to all vectors, just leaves the first two coordinates the same and turns the third coordinate into 0, then what would you guess would have to be the answer to this question? For what vectors x, what would x have to be for this to work? Well, as long as its first and second coordinates are 8 and -5, it wouldn't matter what its third coordinate is, because it would just be getting replaced with 0. Right? So, and it turns out that is how S works, and that's why we got this solution. Take a look at this solution. The first coordinate has to be, oops, that's not what I meant to do. The first coordinate has to be 8. The second coordinate has to be -5, right? Because those two coordinates are going to be left alone. So that's what's going to make us end up with 8 and a 5 in the first two coordinates. But the third coordinate is the free variable. That's the parameter. That can be absolutely anything at all. Well, why is it that it can be anything? Well, because S is just going to turn it into 0 anyway. So in that sense, that's how that ties together. So if S replaces the third coordinate with a 0, then it makes sense now going back to, if this had been anything else, if there had been something here that wasn't a 0, well, then it'd be impossible, right? That's, if you think about what S does, if it turns the third coordinate into a 0 and this had been something else, then this equation would have no solution. There'd be no vector x in R3 that made it true. Okay, so, and here's a picture too of what S is really doing. This is, again, this is another, I didn't draw this. This is just another picture from your textbook. There's a lot of nice diagrams in there. And it just kind of shows you what S is doing. Okay, so let me zoom in a bit since we got the option to do so. So here you've got a point. Okay, let's say that was, actually why don't I use this one because then I won't have to draw across anything. Let's say that is a, I'll draw a bit bigger since I'm zoomed in. I want you to be able to see it. So that's, let's say that's a vector u. Well, it's got an x1 coordinate, probably about here. And then it's got an x2 coordinate, well, about here. And then it's x3 coordinate, well, it's hard to see exactly, but maybe it's about here. But what's S going to do? S is going to take its third coordinate and make it 0, right? So the effect that that has, I'll just erase this so it's not cluttering up the diagram. The effect that that has is it pushes that point straight down. It pushes it down so it's right down here. If it has, because those are the points that have an x3 coordinate of 0. That shaded plane, basically it's the x1, x2 plane, right? It's the set of all points that have an x3 coordinate of 0. S has the effect of pushing vectors straight down onto that plane. Or if they're below the plane like this one, this has a negative x3 coordinate, well, then S has the effect of pushing it up, straight and directly up towards that plane. Okay, but I'll just leave the one label on there just so the picture doesn't get too cluttered. So that diagram is quite helpful. Lets you see visually what S is doing to points. It's just pushing them either directly up or directly down onto the x1, x2 plane. Okay, so you've seen a couple of examples of linear transformation. There's lots of different types, and there's not enough time to go through all of them in this section. We'll see plenty more as the course goes on. But that's what linear transformations are. They're just functions. They're vector functions that have nice properties in the sense that they interact nicely with the arithmetic operations that we have in Euclidean space.